Hello everyone, we are doing occupant modeling workshops and today we will be doing workshop 4. That is on page 16, I believe. And yes, it is on page 16, workshop 4. Now we will be plotting injury channels and also looking at some post-processing. We will be looking at some animations. Now, I have said go to the following directory, the same 50th fast dummy directory, and I have asked that you open the PDF document file named this. And I have already done that, and that document file is this one. And we will be referring to it frequently. Now, in the workshop, I have also said go back to the SLED Learning Aid model directory, SLED Learning Aid. And then I have said launch LS pre-post, and then we'll do some operations. I'm pausing it a little here. Now, if you go to that directory, you can see these D3 plot files. I had already run the model, and these are the D3 plot files which were produced. You can run the same model, dyna.k, separately, and you will get these D3 plots. Now, we have been asked to launch LS pre-post, and from file drop-down menu, this time instead of importing, which we used to read in a dyna keyword file, we are going to open and then LS-DYNA binary plot. And these binary plots are, I'm in the wrong directory for the binary plots, and occupant safety modeling course notes, and then models required to follow course notes, SLED Learning Aid. And here are the D3 plot files. So I picked the first one, D3 plot. If you pick the first one, then all the rest will be read in automatically. So you don't have to pick all of them. Just pick the first one, which is D3 plot. And then the next ones are D3 plot 01, 02, etc., which you don't have to bother about. Now open. And let's auto center and bring it in. Now, this is our model which we have run. And here we are saying just animate to see how the dummy moves. The seatbelt stretch and the airbag inflates. So here we are in the animation panel, and we can just run it. Okay. And of course, this is very fast. We can step through it like here, one step at a time. Okay. And of course, we can slow it down by dragging this button, okay, somewhere here, and still animate, and this will slow down the process a little bit. Okay, now we are going back to state 1. Okay, I have said that the animations don't look the best. In the rebound phase, the dummy is flying off. It is being dragged back and through the seat and everything. But this is just demonstrative. In a real model, it might be much better, especially with the other dummies that we have. So don't worry about that in the rebound phase. Now let me pause a little here. Now the thing to note in this is how the vehicle model is responding. And you can see the vehicle model pitch down this way. It will also drop down because you can see this whole thing drop down. And we'll also show yawing. So I'll step through and watch for drop first. And so this point might go lower and lower and lower. And so just look for drop and you can see it is dropped based on and how low it has dropped. This is a drop amount which I have specified inside the deck, and we can learn that separately, and it has been discussed in my course notes. So I'm not going through that here. Now look for pitching, which is a rotation of the entire thing frontwards. And look for rotation this time, not the drop. And it is not very clear, but you can see an slope of this inclination. It was horizontal before, perfectly horizontal, but based on the pitch value I gave, it is now there is an inclination of these floor pans and this, and so you can know it is pitching. What about yawing? Let us go back, and for that we have to go back to the top view, and you should be able to see yawing, I believe, in this in a clockwise direction seen from the top based on what I gave. So the line is gone from here to here. There is more distance here than here, so it has been yawing. So we can show you this yawing in real motion. Okay, and then your yawing stops based on what I gave in the curve. So anyway, let's stop it here and go back to left view. Now I will show you something more, and that is I'll go to element tools and identify node number. I'll have to put the node number here, and it is 2067556. I just picked a node 67556 and hit return, and this node is on the belt segment from the retractor to the D-ring, So let's rotate it a bit. Actually, the anchor side and the retractor are very close in this model. Usually they are not, but in this model they are very close. And you can see this has come and stopped here, and there is a beam which I have used to connect this anchor point to the vehicle. And also this belt has come and stopped here, and there's a little beam which we have used to attach it to the floor. So this is the belt segment from the retractor to the D-ring. And I've just identified a node here. Now I am shrinking the model a little just to show you the elements. Okay, and what I'm going to demonstrate here, let's go to model, select part, and let's click this out and this belt segment out. Okay, and the retractor is right here. The retractor is right here at a point. Retractor is just a point by definition in DYNA, though it can spool out material and spool in material, and those are discussed very heavily in my course notes for the belt, but we are not discussing it here. But look at the animation, at what happens and what happens during the animation. You can see it's going in. That node came in so much from up there to down here. So what is going on? This node is being pulled in by the pyro pretensioner. The pyro pretensioner. Now, I forgot to discuss the pyro pretensioner in my belt course notes. Okay, it is described very well in the belt model here. If you go into the real deck of the belt model, driver belt model, And we are going to do that soon. If you go in there, it is very well described. But I just forgot to discuss it in my sled model, in my belt model course notes. So let us discuss a little bit about this pyro pretensioner. Okay, you can see again, I will animate again. Okay, as soon as it fires, it pulls in material and it tightens the belt. That is the purpose of the pretensioner. But after that, it doesn't do it anymore. And now, if you go on animating, okay, it goes back up again because now the dummy is pulling. The dummy is pulling, okay, dummy is pulling this belt, so it has gone through the D-ring, it is pulling this, and so it is going up again. Okay, the pyro pretensioner's action is somewhere after it fires, it finishes within the next 10 milliseconds. So by about 25 milliseconds, the pyro pretensioner action is over. Its purpose is to tighten the belt initially, and then when the dummy starts pulling it, the belt starts spooling out again. And you can see it's going up and up because of the dummy pull. Now, in olden times, say about 10-15 years ago, they had only one type of pyro pretensioner, and they used to be inside the retractor. So there was only one type at the beginning, I believe, and it used to be integrated inside the retractor. And after it fired, sensor fired it, the retractor would first spool in the belt material. Spool in. So it's pulling in instead of paying out initially. And then the same retractor would pay out belt material, just as you are seeing it here. So because of this, in DYNA, we always model a pretensioner using a retractor. Okay, now later on they used to have pretensioners not only at the retractor but also say at the anchor. Let's bring back our parts, all parts. Okay, and this part which I had taken out, there can be a retractor now at the anchor. Okay, at this anchor, and there can be a retractor at the side of the buckle. Okay, let's take the shrink off. This is the buckle. The chest belt has gone around the buckle to the lap belt, and this is the anchor on the buckle side, and there can be a retractor nowadays here. Okay, so not a retractor but a pyro pretensioner, not a retractor. Okay, so we can have a pyro pretensioner here and also on the other side right here, and of course in the retractor we can have a pyro pretensioner. I have heard that nowadays they have dual pretensioners. It can be in the retractor itself, the real retractor, but there can be also another one on the anchor side, not on the buckle side but on the anchor side. But it does not matter. In DYNA, we always model a pretensioner using a retractor. Now what do we do here? If it is here, the real retractor, we can have a pretensioner like we have in this model. But on the anchor side, what we do is we put in a fake retractor. That means we model another retractor just to model the pretensioner for this part. And that spools in the material on this side, behaving like a retractor. And we give a very stiff retractor function because otherwise that retractor is going to spool back material out. But in the real pretensioner on the anchor side, it cannot spool out anything. It just pulls it in and keeps it there. There is no real retractor on that side in the real vehicle. So we put in a fake retractor with a very high stiffness curve, and we use that to pull in the material on the anchor side. This is just a way of doing things. But the main purpose of telling you this is the following. In DYNA, the pretensioners are always tied up with some kind of retractor. In this model, there is only one, and that is on the retractor itself. And that is what we are going to discuss now. Now, let us go to the deck and look at this file, edit this file, which is the driver model file. Okay, and we are right at the top, and now let's look for the string pretense. Okay, now find next, and immediately it comes to this pyropretensioner pull curve. That is what has come up first in the deck. Okay, this is being referred to by the actual pretensioner, but since it has come up, let's study it a bit. What does the pretensioner do? It will follow this curve. Okay, sorry, not this curve. This is a retractor force curve. I'm sorry, the one below. Okay, this is the pretensioner curve. And this is the idea of the curve. It says that after fire, this zero is not time zero in our run. This zero refers to when the retractor is the pretensioner is firing. It might fire at 13 milliseconds. Okay, so this 0 refers to 13 milliseconds. This 10 refers to 23 milliseconds because you have to add it to the fire time. Okay, it gets automatically added. And where that is, we will look. Okay, but it says from 0 to 10 milliseconds after fire, it will pull in material from 0 to 90. This pretensioner here pulls in 90 millimeters of belt in 10 milliseconds. And then it keeps it constant and doesn't pull in anymore. So I've given a high number like 200 milliseconds. My simulation is only up to 150 milliseconds. So I've given 200. And it keeps it here. So this is the curve 2067002, which is being referred to in the actual pretensioner. Now, remembering this and remembering the curve number, okay, we find next. Of course, it is here, right here, and then we come to this block, which is element seatbelt pretensioner. And this is the curve, and this is the keyword, element seatbelt pretensioner. And here I've annotated it perfectly so that you don't have to look into the manual. Okay, the first thing is seatbelt pretensioner ID. Seatbelt pretensioner ID, and this is just an ID for this pretensioner, just this pretensioner. There's only one here, so this is just an ID. And the type is 5. Okay, we are using type 5. There are other types which I have not investigated too much into, but this type 5 does our job. And you can use your imagination to use type 5 quite well. I've said equal to 5 for pyropretensioner with limiting load for the pretensioner. And what that limiting load is, we will discuss. And then we come to a sensor, 2067001. And that sensor will tell us when the pyro is being fired. Okay, and I have written here, let's take this out of the way. See sensor ID 2067001 under star element seatbelt sensor for pretensioner fire time. I've already told you that. Now this is important. It is the seatbelt retractor ID. This pretensioner we are discussing is inside this retractor, And in this model, there's only one retractor, and the ID is 2067111. And we'll come to that soon. This time, you don't have to really bother about that right now. We can keep it 0. And remember the curve ID, the pull curve ID 2067002, which we studied. So from 0 to 10 milliseconds, it will pull 90 millimeters and then hold it. That is that curve. Now this limiting force is very important. Okay, and this depends on the type of hardware, the actual pretensioner you are using. Now the pretensioner fires and pulls the belt. Now it cannot pull so hard that the belt will break a person's ribs or bones. If there is no limiting value to the pull, it might tighten so much that it might break a person's bones. And we do not want that. The actual crash might not be doing anything to the occupant, but the pretensioner has pulled so hard that it has injured the occupant. And we do not want it. So I think in most pretensioners, actual pretensioners, there is a limiting value that if the force comes to that value, the pretensioner will stop and not pull anymore. In our model, we have put a limiting value of 2.5 kilonewtons. This is in kilonewtons. Okay, so I've written here limiting force for retractor beyond which it will not pull. So once it hits 2.5 kilonewtons, it will not pull. But this is a number you cannot use arbitrarily. You have to ask your supplier what the limiting value is. And I believe your supplier can tell you what that is, and you can put that number here. Here we have, for example, we have just used 2.5. Now let's go to the retractor. Okay, let's go to the sensor. Okay, 2067001 first. And control find, and let's do this element seatbelt sensor. Control C. I've asked you to search for this, and so Control V. Find next. Element seatbelt sensor. Okay, and element seatbelt sensor. Now there are two sensors here. One of them is being referred to by the retractor itself for the retractor operation, not for pretensioner. Okay, the retractor lockup time is 1 millisecond. Okay, and SBSID is seatbelt sensor ID. Okay, and this is used by the retractor. And this one, 2067001, is being used for pretensioner firing. And I have said that the pretensioner fires at 13 milliseconds. Okay, now when it reaches this, it knows that the pretensioner fires at 13 milliseconds, and from there onwards, the curve ID, which we were referring to, the pull curve, that time will be added to this. Sorry, that time will be added to this, and then it will pull accordingly. So this is the element seatbelt sensor. Okay, now let's go back to our pretensioner and look at this. This is the ID which will be there, and let's go to pretensioner again. Okay, reach. We have come back to the pretensioner curve, and we are going in again, and we are here. And remember the sensor ID 2067001. This is referring to that. Okay, now let us study the retractor itself. Okay, 2067111, and this is the element seatbelt retractor inside which the pyro is there. Okay, and this is the retractor. We are not going to study the retractor right here because the retractor is well discussed in my course notes. So that is not what I am going to discuss here. But I have just told you that our pretensioner is seated inside this retractor, and this retractor is the only retractor, so these IDs match. So it is going to be inside this retractor. Hopefully the basics of the pretensioner has been understood. And I did this only because I had forgotten to discuss this in my belt course notes. So let's close this for now and go back to the workshop. And we are going to plot in LS-DYNA, sorry, not LS pre-post. Okay, we are going down to time 0 again. Okay, and we can auto center, it doesn't matter. Now we'll go out of this and we'll go to post processing here, post. Okay, and this comes up, and because of the directory I've given you, this directory, the ASCII files are already there. There is joint force, and then there is the seatbelt output file, and then there is the section force file if there are any. There is a node out file. So all that is already there because I ran the job. So we are in that directory, so we can directly read in the ASCII files. So let's click ASCII and follow the document a little. The document says pick node 1, first of all, in node out. Okay, let's see accelerations, node out, but nothing has been read in. I've just clicked node out and say load. Now it has come up. Okay, all the node numbers. Now the document says node ID 1, but because we offset the dummy IDs in this example by 1 million, it has become 1,000,001. And that is the node ID for the head accelerometer. Okay, if you plot, let us go to element tools, identification, and let's put in 1,000,001. I hope I'm right. Okay, no, 01. I think this is right. Okay, and so it is right in the head. Now let's do some more. 1787, and this is somewhere inside the chest. Okay, and let's do, these numbers are known to me, and this is the pelvis. These are accelerometer node IDs, so we can get accelerations, just to let you know, have an idea. And you can remove these parts and see how the accelerometer is. Okay, we are not doing it here, but we are going back to post-processing and ASCII and plotting, picking this node. Okay, and now we have to see what we want to plot, and we want to plot X acceleration, and let's put Y acceleration and Z acceleration all together and just say new. Okay, and we got all the accelerations, but this is very noisy, so let's filter it. Now press the filter button, and here it comes up First notice the time unit, and it comes up default as milliseconds, which is our time. Okay, if you pull this menu, you can go to second, and you can go to USEC, which I'm not sure what that is. Okay, but mostly we need either second or millisecond, and it comes as millisecond, so we don't do anything. And then the frequency, okay, and it is default is 60, but there are other ones here which we can click and bring. But the main thing is, if you do not have the frequency you want here, just type it in here. This is what will LSP post will take, this number here, not what is here. Okay, it can be anything here, but whatever you type in here is taken. Now in the filter, first it is none, but we have several types, SAE and Butterworth. These are the two most important ones for us, SAE and Butterworth. Now SAE is the same as CFC, okay, and that is the one that automotive engineers use most. Now SAE and BW are all very close, but the numbers that you use, the filter frequencies that you use, are not the same. So what is the relationship between SAE, which is CFC, and BW? Just remember one thing. That is, if you take the frequency of BW and multiply it by 0.6, then you will get the SAE frequency. And the filters should be more or less the same, but the numbers are different. So if you have BW300 and you filter a curve and save it, and then you go back to the same original noisy curve and use SAE 180. Why 180? Because in BW you used 300, and multiplying 300 by 0.6 will give you 180. So now you are filtering the same curve using SAE 180. Put 180 here, and you filter it and you save it. Now you overlay the two curves, the BW 300 curve and SAE 180 curve, and you will find them to be very close. Okay. Now, in my experience with the models I have seen that for CAE, just for CAE, not for actual crash test data, if you use 180 for these channels, if you use SAE, not 180, but 108, okay, we had 108 here also, so we could have picked, but I have just typed it in. Then you get quite smooth curves which can be used. Okay, I've done that. So these are the curves, X, Y, Z's. Okay, now there should be a legend here. I'm not sure why the legend is not coming up. So let's go to title and modify curve legend. Okay, and there should be some legends coming up. I don't know why on that side. Oh, legend. Okay, this had to be highlighted, picked, legend, here. Okay, it was not picked. It should be picked by default, I thought, but I don't know why they have turned it off. Okay, so now this is acceleration and this is time. These accelerations are in millimeter per millisecond per millisecond. Millimeters per millisecond square. Okay, now we have to turn it into G's, and we'll do that in a moment. But let me tell you before that, let's go back to filter. Okay, and we have, why did we use 108? Because I actually wanted to use BW 180. That is a good filter for me, 180. So we multiply 180 by 0.6 and I got the number 108. So I've used SAE CFC 108. Okay, that's all I've used. Now we can turn all of these into G's. How do we do that? We have given in my notes, if you go to workshop 4, okay, and I've given some of those steps before, and I've discussed some of this SAE CFC filter frequency and 108 and all that. But come to this section, okay, we have our acceleration in the unit millimeter per millisecond per millisecond, millisecond square, but break it up like this, millimeter per millisecond. Now millimeter per millisecond is the same as meter per second. Okay, millimeter per millisecond is the same as meter per second. So we do not have to change the first part, the velocity part, we do not have to change. But the acceleration due to gravity is 9.81 meter per second, whereas our unit is millisecond. So how do we change this acceleration due to gravity into per millisecond? We divide it by 1,000. And so G in our units is 0.00981 millimeter per millisecond per millisecond. This is the same as this, so we don't bother. We only change this. That is how you have to understand this number. Where does it come from? Because in MKS it is 9.81 meters per second square, and so G in our units is 1,000 of that, and 0.00981 millimeter per millisecond per millisecond. Now, in our curve, if we divide these ones by by 0.00981, we will get acceleration in G's. So let us do that by scaling. Okay, and we pick all of them and we do Y scale of. Now one more thing, we have to divide by 0.00981. So if you take a hand calculator and divide 1 by 0.00981, we will come up with the number 101.937. Okay, I know this because I've done it many times. Divide 1 by 0.00981. Okay, 101. And now we are scaling all these numbers by this, and we say apply. We have picked all of these three curves. Okay, and now we say it is all gone outside of the screen. We say auto fit here, auto fit, and we click and it comes back, and these are in G's. These are in G's. So we have filtered each curve and we have multiplied each curve by 101.937, though we could have done it later. Now let us do resultant. Let us do the resultant, and to do that we go into Opper. See, scale was here, filter was here. We first filtered, then scaling, okay, by multiplying, and that's where we are. Now we go to Opper to do, which is operations, and here we have resultant 3, the resultant of 3 curves. If you had 2 curves here and you wanted to find out resultant of 2, you could have done this, click this. But we are doing resultant 3. Okay? Now curve 1, you highlight and click this. Curve 2, it has already gone there. Highlight Y and it has gone there. Curve 3, it is already ready for it. Curve acceleration, Z acceleration. Now we apply. Okay, and this is the head resultant curve. But remember, you have to filter first all the curves, all the three, before you can find resultant. Do not try to find resultant on the noisy curves. I have written that in my course notes, in my workshop somewhere, that you first filter and then operate on them, then try to find resultant. Of course, the scaling you could have done now instead of doing then. That is fine. You can do scaling finally. But to find resultant, you have to do filter first. Okay, so this is the head resultant. And of course, you can do the chest resultant using this node, and the pelvic resultant doing this node. Okay, so let me pause a little for the next step. Now let me tell you something before I go to other ASCII plots, and that is, this is my animation file which I've read in, which was already there, which we read in before. Now let me say that we can superimpose the original model onto this animation file. This is just animation, okay, but we can bring in the original file that we ran right on top of this. And how do we do that? In this case, file menu, and I said before that when you read in a keyword file, you import, okay, this. But in this case, when you are superimposing, again open. But remember, we used open to do binary plots, okay? That is how we got to the animation. But here, open and open the DYNA keyword file. So you are first read in animation, and we are trying to bring in the original DYNA keyword file which we ran to run this job. Okay, and that is what, and we are going to superimpose it. The node numbers are exactly the same, everything is exactly the same, so we can superimpose. Now it brings us to this directory. LS-Prepose got us this directory, and which is the file we ran to get the D3 plots? It's the dyna.k master file. So we click this, okay, and we say open. Open. Now it brings us back to the model, but it asks us this question. Is this the same model as the D3 plot file? I mean, the English is not that good, but it means LS-Prepose is asking us, the file that we chose, dyna.k, is it the file that was used to produce this D3 plot files? We have to say yes or no, okay, at this point. If it is the same file, we just say yes. Okay, and now there are some errors coming up because of something else, but it doesn't matter. We have, I think, imported the model. Okay, and let's see, select part. See, there are many more things now. Beam, shell, solid. In animation, in D3 plot, we had only beam, shell, and solid, but we have a lot more things now. Okay, we can actually analyze this model completely. And let me take out some of these parts now. Okay, let's keep the beam. Let's take the seat belts away. Let's keep the discretes. Let's take the masses away and the CNRBs away. So here we are, and I will zoom in to the chest area here, the chest area, okay? And I've rotated it slightly. Now just to show you where we are inside the chest, okay? We are inside the chest. I just clicked up shell to tell you what it is, and solids, you know. So we are somewhere inside here. So let's take the solids away, and we are here. Now this is the chest potentiometer. In the real dummy, the same thing is there. And there is a spring here, a rotational spring. If you study the dummy file very carefully, and I'm encouraging you to study the dummy file for all these things, but there is a spring here, rotational spring, of very low force value, very low. That means it just rotates, and we are using this just to measure the rotation of this beam. And this part, okay, this tip, the red tip here touches the front of the chest. So what happens is, when there is chest compression, when the belt is forcing it to move, this will be pushed backwards and this whole thing will rotate about this. Okay, so let us see whether we can actually do it and see what is going on a little bit. We are going back to post for animation, and let us follow this node here, okay, and apply. So the purpose of following it is to keep the whole thing on the screen so that it doesn't move around. Everything will be, all the animation will be about this. So let's see what happens, okay? Let's see, done. And let's step through. See, and it is rotating about that point. Okay? Even in the real dummy, something like this is there. And the person who modeled this dummy initially and gave it to me, he had put what the real dummy has. Now here there is some sensing device inside the real dummy which measures this rotation. It just measures the rotation. Okay, if you plot the, let's say, the shell here, okay, and you can see the same compression, chest compression, the belt is pulling it. Okay, let's zoom out a little bit. The belt is pulling it, and that's why it is pressing on that. Okay, let's take out this airbag first, and this airbag, okay, just to show you the chest compression. It is squeezed, okay. Okay, it started moving because I clicked the wrong button, and okay, so you can see this inside, okay. As it presses, it will press and it will rotate, and that beam is rotating. Okay, so you can study this a little bit. Let's take shell away, and this is what is going on. But the dummy chest compression is a linear value. Length, how much has it compressed? 30 millimeters, 40 millimeters. That kind of measurement is there. But all that your chest potentiometer is giving is a rotational value. So there is something called a linearizing factor, which converts this rotation into a linear value at this point. This is also going on in a circle, kind of, but it is more or less, we take it to be straight, and that is the chest deflection. And even in the real dummy, that is going on. They have a linearizing factor to convert the rotation here into a straight line compression at this point. Okay, based on that, we are going to do the chest compression. That is why I had to explain this to you. Okay, so let us go back to post and ASCII, and this is given in the dForce file, discrete element force. Now why are we doing discrete element? Because this spring is a discrete element. It is a rotational spring, but it is discrete. Okay, defined as discrete element. Now let us load this file. We already have the output. Okay, now This usually comes up as translation, but because there are many other springs which has produced all these translational values, okay? But we are interested in this. So what we do is we change this to rotate, okay? Rotate. And this spring ID, I believe, is 1,010,000 rotational R. We have to pick this, okay? And then we have to pick relative rotation from down below. Relative rotation. And now you say new, and it comes here. But this is just angular motion here. Relative rotation, these are in radians. Now what we have to do is scale this and put a value of the linearizing factor for this dummy. I've said at the top of page 18 is 145. Okay, and now we multiply, scale, and it say auto fit. And in this dummy, the chest deflection is around 40 millimeters. And this is the way it will plot. Okay, so we have plotted it. This is how the chest deflection is plotted. Follow the manual. Now, one more thing I have to show you, and that is plot the upper neck corrected moment. Corrected moment. Okay, so let us first go to model, select part, and bring everything back, okay, and auto center, and let's go to this part of the neck, okay, left view, zoom in here, okay. Now in the real dummy, let's take the head skin out of the way first. And this is simplified, okay. Now in the real dummy, what happens is the neck, you know, there is a bolt which, sorry, there is a bolt which goes through the upper head assembly and the neck here down below. And this bolt is where they want to measure the neck moment. The negative neck moment, which is so dangerous, it is measured at this bolt. Okay? But unfortunately, if you check the real dummy, because there is a bolt going through this point, they cannot place a load cell there. They cannot place the load cell there. So they place the load cell 0.7 inches above this bolt, and it will be somewhere here. Okay, it will be somewhere here. The load cell is here, but they want, and that is the only value they can get for neck forces and neck moments, the loads, whatever the load cell gives. But because they are measuring it higher, they have to correct that so that they know what is here. This is the real point of interest, but they are measuring it 0.7 inches higher. And 0.7 inches turns out to be 17.78 millimeters. And this height of 0.7 inches is the same for all hybrid 3 adult dummies. The 5th percentile, the 50th percentile, and the 95th percentile. This lever arm is the same, 0.7 inches, 17.78 millimeters. So whatever moment comes out at the load cell has to be corrected by a certain amount. And what is that amount? We also find out the Fx, no, upper neck shear force, Fx, multiplied by 17.78, this lever arm. Okay, so you can see the moment, there's a question of a moment coming in. Okay, and then whatever that is, you subtract it from the neck moment that the load cell is giving. you subtract it. Okay, there is a way to do it, and I think I've defined that in my dummy user manual. I've told you how to do that. You can go through it. Okay, that is for the real dummy. That is what they are doing in the lab. They are measuring the neck moment here, but they also have the neck Fx shear force. They multiply Fx by 17.78 millimeters, and they subtract it from the neck moment as given by the load cell. And that is the moment here, which is what they want. Now, we have a CAE model, and we have a joint here. Okay, so we can take advantage of this fact that we are working with the CAE model and extract the moment right from here, right from this joint. Okay, and if we do that, we do not have to do any correction. And that is what we are trying to do here. We are trying to directly access it from here because it is a CAE model, so that we do not have to do any correction. But if you extract it here from here and plot it, and if you extract it from the load cell and correct it and overlay it on the moment that you got directly from here, they should be very close. They should be very close. Okay, so because it is a CAE model, we are doing it from there, and the method I've given here is post, and then we go to ASCII, and then we go to joint force here. That is where the results are, and we load it. Okay, first these joints come up, and that is this default J force, joint force, but we want moments, and therefore we do stiffness R. Remember, there are joints and there are also joint stiffnesses which are placed together on the same joint, and for moments we have to read it from the stiffness file. And what does the workshop say? It says extract it from the stiffness number 1,044. 1,044. That is the stiffness J stiff R on this joint. Okay, and we do this, and then the document says plot theta moment total. That is about the y-axis. Okay, so it goes like phi is about x, theta is about y, and psi, psi is about the z-axis. We are interested in the y-axis, so we say theta moment total. Okay, and now you say new, and this is the corrected upper neck moment. Corrected. But if you save it and you go through the dummy user manual and do the extract it from the joint, actual joint, which is also there in this model, and you correct it with fx and all that, multiplying fx by 17.78, subtracting it, and overlay it, you should be getting almost the same. So this is the end of workshop 4. You can do other channels also. Okay, I think I had another thing like plot femur forces. So let's do the femur force also. Okay, and the femur forces are coming from the joint force also. So we go back to joint force, but this time we are not interested in femur moments, but femur forces. And the manual says pick joints 24 and 25, which is 1,024 and 1,025. Okay, 24, and this is for the left femur. And then We also say control button and pick this. If you want to pick 2, pick this. And the femur force is in the Z direction, Z force, okay? Z force. And now we say new, okay? And now of course we can filter this SAE, and let's type in 108 again, okay? And let's say apply, and these are the left and the right femur forces that you'd be interested in. So we have done all this. We have done the accelerations of the head, chest, pelvis. We did the chest deflection according to the manual. We did the corrected neck movement, upper neck movement, which we are interested in, and we have also done the femur forces. So you get the idea of how to do all this. So if you now follow the dummy document and plot everything, you will get everything you are interested in. So that brings us to the end of workshop 4.